Hello there, you're very welcome to this, the third in the series of webinars from Impedans. This is the final webinar of 2022, so we would really appreciate your feedback and comments on the webinars to date, and indeed what you would suggest that we may include as topics coming into 2023. If you want to enter some comments, please have a look at the chat section on top, the chat button. You can either put comments in here or you can enter questions for today's webinar. At the end of the webinar, Tom will accept questions, so please keep putting them in as we go through and we'll be delighted to answer. If we don't get to any of those questions, we'll get back to you in due course via email. And as always, you'll receive a set of slides from today's presentation and also a copy of the recording. This may take about 24 hours. But as I say, please do ask questions in the chat box above. Now I'd like to introduce you to our host again today, which will be Dr. Tom Gilmore. Tom has over 13 years experience both in academic and in industry. So today promises to be another enlightening presentation, and I'll hand it over now to Tom.
Thanks, Declan. I'm going to turn off my camera to save a bit of bandwidth, and let's get started. I'd also like to remind anybody, we have many non-native English speakers in our audience. If you click the three dots up above and you can enable live captioning, so then you'll get real-time subtitles in Microsoft Teams. Okay. So let's get started. In terms of the agenda, the first 15 minutes are going to give an intro. Our audience, spans a wide range of people with different levels of experience. So I want to give some level of introduction to, measuring RF in general. So I'm going to talk about VI probes and compare them with kind of directional couplers and other similar technologies. I am going to mention the Octiv technology, which Impedans provides. I'm going to talk about a high-level overview of, how you calibrate a VI probe and what that enables. I'm going to spend maybe just 5 minutes on the basic applications, such as generator calibration and matchbox characterization. We'll go through that quite quickly. And then the whole rest of the presentation will be on various applications when it comes to plasma monitoring using, VI probes. From the simple things enabled by just knowing the voltage and current after the matchbox, all the way up to, being able to do real-time fault detection, endpoint detection, chamber matching, and so on. Right, so let's get into it. Let's start off by looking at, directional couplers versus VI probes, because I think many people may have used something similar to directional coupler technology and have not used a VI probe. Just a very simple preamble, like, RF measurements, what matters. So if you can measure the voltage, current, and phase in an RF network, you're going to learn pretty much anything about it. With these, we learn about the power delivered and we learn about the load impedance. And these matter differently, on the side of the generator and match and on the side of the plasma, and we'll go into all of that. There are many sources of error in RF measurement. So like, the linearity of the measurements versus the signal or power level, the frequency errors. So what are the measurements like versus frequency? What are measurements like versus VSWR? What about the temperature of the sensor you're using, the local humidity, and so on? And power accuracy can change with load impedance. So, RF measurements are actually quite complicated. So let's start off with the most simple measuring device, the directional couplers. So put simply, a directional coupler measures forward and reflected power on a transmission line, and it has high directivity and isolation. So if you know the forward power and reflected power, it means you know the total power, the return loss, and you'll know the standing wave ratio of the load. So this is a very old technology, quite simple, but has a couple of drawbacks. Usually power measurements are only accurate over a limited impedance range or a limited VSWR range. The accuracy tends to be impacted by temperature and humidity. All this can be compensated for, and they can have complex designs, especially for high voltage applications. Some of the key issues are, you don't get good power measurements when harmonic content is present, and I'm going to show data examples of that in a few minutes. And you also get power loss at the ports. So one thing to note if you're using this type of technology to calibrate a generator or something is that a few watts are absorbed by the coupler. So that means, if you calibrated a generator to the point where, it says 0 watts according to your directional coupler, it's actually absorbing a couple of watts, so there's still some power. So in other words, like, never trust a 0 output on your generator, whether it's on output power or reflected power. Never trust a 0, okay? If it's being calibrated with directional coupler technology, there is still likely power there. This is something we see surprisingly often. All right, so VI probes, what are they? So a VI probe measures the voltage and current at any point in the RF network. And if you do that correctly, you also get phase information. And then once you have that, you get the power and you get the complex impedance delivered to a load, pretty much any load, by the way. They can be installed before or after the matchbox. And in terms of the technology, it's based on remote voltage and current pickups. So I've cut off some text there, but you can see a diagram at the bottom. The idea is that you have some sort of, electric field pickup, which is simply a capacitor, and you have some sort of current loop to pick up the, magnetic fields. Just going a bit further, how the technology would work, so you have a sensor which has a transmission line through the center. You have these remote pickups. These are usually, analogs. These are analog signals. They're amplified. You have an analog to digital converter, and then you do a lot of analysis on the waveform that comes through, like fast Fourier transforms and so on. And that's how you then start getting information about the RF in the locality. So there's sort of pros and cons to VI probes. So some of the advantages are power and impedance can be measured over a really wide range of loads. So even outside of 50 ohms, you can get good power and impedance measurements. You can monitor multiple frequencies simultaneously, which means you can measure the power and impedance of each frequency individually. This is quite important when it comes to plasmas, because plasmas produce harmonics. Okay. And this is only possible, by the way, if you use the VI probe technology and you use Fourier transforms on the waveform. There's an alternative method called peak detection, but this has the peak detectors have the same issues as directional couplers. And the remote pickup means that power measurements can be precise from milliwatts to tens of thousands of watts by controlling the pickup distance and sensitivity. So being clever with the design means you actually get a much wider range of applications. Some of the challenges, though, as I mentioned, you need to know the phase in order to know the power. So the phase accuracy is critical, especially when the phase is near, plus or minus 90 degrees between the voltage and current, because the cosine of the phase is how you get the power, and the cosine changes rapidly near 90 degrees, plus or minus. Another thing is there can be crosstalk between the voltage and current pickups, but this can be calibrated out if you're clever with the calibration. Okay. I want to show you some data then, comparing directional couplers to VI probes that we took in the lab here. So simple setup, RF amplifier, directional power meter. I'm not going to mention exactly what it is, an octave and a reference calorimeter. So first, putting a sine wave into a 50 ohm load, everything was within spec. You get measurements within 1% of the calorimeter. For those of you who don't know, calorimeters are very good at energy measurements, so that's very good at power measurements. So 50 ohm loads, they all behave quite well. Now let's do a thing where we put in, introduce harmonic content. So harmonic content can be present because of emissions from a plasma. They can be present due to generators slowly failing. They sometimes then emit some harmonic content. We put in a square wave to simulate harmonic content. So all the odd harmonics now have some power dissipated in them. And with a VI probe, you can separate all that out. So you can see then, this is the total power here is 185 watts, and 152 watts are measured at 13.56, and there's power dissipated in all the different harmonics. So let's show the data. So the calorimeter was measuring 185 watts total. The octave was like a VI probe was measuring 152 watts in the fundamental frequency, the 13.56, so not the harmonics yet. But the directional coupler, which doesn't try to split out frequencies or anything, only measured 130 watts, so it is completely wrong. So harmonic content damages the data basically. And just to note that when you actually add up all of the harmonic content, so if you add up the powers and all the different harmonics, it actually comes very, very close to the calorimeter. And this is considering this is only 15 harmonics. There's quite a lot. There's quite a lot more in the square wave. There's an infinite amount. So let's go into VI probe technology. I'm going to briefly mention, our VI probes, our calibration techniques, and our features before we go on to the plasma applications. Starting quite simply, what does a VI probe measure? So it measures voltage, current, phase. You get the forward reflected and delivered power, and also you get VSWR. I forgot to mention that here. You measure the complex impedance of the load. You can measure harmonics, and you can also, like, obviously, you still have the original waveforms available. Each of these enables pretty powerful applications if you use them intelligently, and I'll show examples of this later on in the slides. So, for example, using just the voltage measured on a VI probe, you can get information about the ion energies inside, what's processing a wafer. With the current, you can get the ion flux, or in other words, etch rate and dep rate. With the phase, you can do things like endpoint detection, although all of these contribute to endpoint detection. For forward reflected and delivered power, you can look at matchbox efficiency, you can do tool matching, and if you use some simple models, you can actually get plasma density and electron temperature, provided that you're taking measurements, outside of the 50 ohm region. I'll go into detail soon on what the 50 ohm region and non-50 ohm region is for those of you not familiar. Complex impedance gives you plasma repeatability. So, making sure your plasma has the exact same impedance every time. You can ensure that the plasma is the same every time, and that therefore the processing is the same. Again, I'll show examples towards the end of this. With harmonics, you can do things like fault characterization. So not only, detect if the plasma is different than it should be, but you can even identify what the fault is if you're intelligent with the data analysis. Okay. With the waveforms, the voltage current waveforms, from a plasma, they're not sine waves. The plasma actually produces its own RF. And with that information, you can get plasma density and electron temperature. Or in other words, a VI probe can be like a Langmuir probe if you use the data intelligently. Again, I'll show real examples of that at the end of this presentation. And then finally, you can do things like arc detection if you have a high-speed VI probe. Okay? So in order to enable all this, you have to calibrate this probe. Okay. So I've mentioned earlier the importance of these things measure power and measure impedance. Obviously, you have to calibrate this sensor so that it can measure those things. Otherwise, it's just measuring, electric and magnetic fields in some way. All right. So I'm going to give you a very high-level overview of how you calibrate a VI probe. I'm leaving out a lot of details, but so one thing is you have to calibrate by temperature. Because you don't want that the sensor gives different measurements depending on the room temperature or the temperature of the cable if you're running high power or so on. It needs to be able to work at different temperatures. So we calibrate our sensors from room temperature to ADC in a special temperature humidity chamber. So all our sensors go through that. So that's like something you need to do with a VI probe. You also need to calibrate against impedance, so you need to calibrate against the vector network analyzer. So there's a reference vector network analyzer. You have different loads available, and then you calibrate the sensor against the VNA. And you have to take a lot of care when doing this. You have to take care with the setup for repeatability, like using torque wrenches and so on. And you also have to make sure the calibration plane is flat. That's a trade secret. You can imagine I'm leaving out a lot of information here on how we exactly do things, but you get the idea. If you do this successfully, you can make it so that your VI probe has the same kind of accuracy as like a VNA, but much simpler to use. Okay, and then of course you need to do a power calibration, and that's typically you use calorimetry for that. So for our sensor, we calibrate at the fundamental frequencies and the harmonics, and also a band around the frequencies because these days you use what's called frequency agility for fast tuning. And when all these calibrations are complete, you must then verify that the calibration was successfully transferred to the unit. So you have to do verifications afterwards at different loads, different powers, and so on to make sure it's good. And what's nice about all these techniques is as new calibration standards that are better, 0.1%, 0.01% accurate, as these come on the market, you can transfer those to the VI probes. So the VI probes improve in step with VNAs and calorimeters. So the overall result of doing these calibrations, if you do them right, is that you get a compact measuring device which has the impedance measurement accuracy of a vector network analyzer and the power measurement accuracy of a calorimeter, except you can use them in the real scenarios, like with the real powers you use and so on. I have just 2 slides on, the Octiv sensor that we have, but just again to mention that you can, with a VI probe, you're no longer restricted to just getting good measurements in 50 ohms. You can get power measurements over, the entire area of a Smith chart for all sorts of complex impedances. And you can get these impedance measurements at, real powers, like, if you run at several kilowatts or tens of kilowatts, you can really characterize your matchbox or check your generator at these sort of powers. You can also do this rapidly. So, like, with a VNA, it's a very offline tool. It's quite slow to use, but these VA probes can go quite fast. So our standard VA probes can report up to 500 times a second if you want. Adjustable. Yeah, and you get more communication options. I've seen people use VNAs that are old and they have to use a floppy disk to get the data and transfer it to a computer to map out, the impedance of a plasma or impedance of a load. So just to add a lot of convenience. The other thing to mention, anything I talk about today, there are technologies that are capable not just for continuous RF, but for pulsed RF. So VI probes can work fast enough and can handle, various pulse frequencies and duty cycles and take measurements under those sort of conditions. So this is more modern tools, use pulsed RF. Anything I mentioned here is possible under that. Okay. So let's move on to some of the simpler applications of VI probes, and this is monitoring the RF network. Okay. So I want to give a very simplified view of what I'm referring to as an RF network. Okay. So you have a generator, you have a cable or transmission line, you have a matching box, you have another cable or transmission line, and then you have a plasma reactor. Okay. And it's important to note that every single part has an impact on the plasma, and also the plasma has a return on every part as well. Okay. So like we always talk about generators and matchboxes, cables really matter, plasma really matters. You actually have impacts on all of this based on the wafers that go into the plasma, which people may not realize. Okay. So today when I talk about 50 ohms, if I mention that, I mean the region from the generator to the input of the match. That's called a 50 ohm region. In here, the impedance should be 50 ohms real and 0 imaginary. Okay. That's what generators are designed to output in. And then there's what I call what the industry calls the non-50 ohm region, which is this, after the matchbox. In here, you can have any complex impedance. You could be at, 10 ohms real and 50 imaginary, or it could be nearly an open, nearly a short. It could be anything in here. This is much more challenging to measure. I want to give a couple of kind of pointers and rules of thumb fairly quickly here. Obviously, if you're calibrating a generator, you generally put a VI probe as your reference right at the, right here, and you calibrate the generator. But in a fab, you might want to think about it a little bit differently. So, for example, I mentioned that cables, cables are an important part because you actually get power loss in the cable. So if you're in a fab where you have a generator in a sub fab and you have a matchbox, a floor on a different floor, you have a very long length of cable. And even if if you calibrate your generator at the input, that's not what's reaching your matchbox. You could be losing up to 10% of your power into the cable, believe it or not, if the cable's sort of a few meters long. So a general rule of thumb is, if you have a subfab, you should calibrate the generator power to the input of the match, but you should also make sure that the generator sees 50 ohms from its point of view to have the minimum reflected power. Reality can be a bit more complicated than this because RF transmission lines are non-intuitive, but this is something you should consider. The other thing I want to mention is, people care about, my generator needs to be 1% accurate or 0.5% accurate, but then they're not thinking about this cable, which would be draining 10% of the power, and they're not thinking about the matchbox, which has its own efficiency. Like matchboxes have fans for a reason, they have water cooling for a reason. Power is lost in there, and the power is lost depending on the plasma and depending on the wafers. Okay, so like your matchbox could be 5% efficient and 10% efficient and 20, you could be losing 5%, 10%, 15% or more power into the match, depending on what process you're running at the time. So people fret a lot about this 1% at the generator, but there's actually 10, 20% margin of error on this side in terms of power delivery. So, ideally you actually measure power that's really being input to plasma, and that gives you much better results for like tool matching and so on. We'll go into that a bit more later. Let's talk very quickly about matchboxes. You know, the plasma normally has an impedance somewhere in the Smith chart. So in this example, it's here. This is really from a plasma. I've seen plasma impedances here and here, and they can be anywhere on the Smith chart, okay, depending on the tool type and the gases you're using and so on. Your matchbox will have what's called an impedance range. So as you all know, a matchbox has a tune and a load. Like usually it's two capacitors, and they can move between different points. Using a VA probe, you can actually map out, what the impedance is of the plasma. We have a video on YouTube about this. You can contact us if you want us to send a video on how exactly to do it. But essentially, you actually run things backwards. You go power supply to the output of the match, and then the input of the match is connected to 50 ohms. So you're looking, kind of backwards through the matchbox, and you move your both tuning caps from start to stop and start to stop. And this plots a map of your matchbox, and your plasma impedance should be within this map. And one critical thing is if you're running new processes on old tools, you can't guarantee that your matchbox is still matched to the new plasma impedance. So you may measure the plasma impedance and it's out here, and this matchbox won't reach it. So that means you'll never get, you'll always have reflected power. You'll have common matchbox failures. You'll have matchbox overheating, like runaway effects, like thermal effects, and so on. So using a VI probe, you can very rapidly map out a matchbox impedance range. You can check the plasma impedance, and then you can, if you have the capability in-house or you contact your supplier, you can modify the match so that this impedance range moves, to match your plasma impedance. We're actually going to send out documents in a few weeks on how to do this mathematically. We'll send out some kind of how-tos on this. Similarly, doing the same process by looking at, having constant forward power on the RF side, on the generator side, and looking at what comes through the other side, you can also match out the matchbox efficiency as a function of the matchbox range. So in different parts, I have different efficiencies. In this matchbox, it went from 80% efficiency to 50%, depending on where you were on the map. So this could be good to know. Like you could be operating in a regime where a huge amount of power is lost in the match. It's overheating a lot. It's being replaced a lot. Where all you need to do is switch to a slightly different matchbox, and all your matchbox problems go away. Okay. We've had feedback from quite a few customers on this. Matchbox mapping is usually done using a vector network analyzer, which means you're mapping it at like 1 watt because that's all it can output. And it's a very, very slow process because VNAs are not typically very user-friendly. Like you have to do everything manually on this box and export data from it. And I've heard that matchbox mapping could take up to 2 days if you're doing a very serious project. But customers have switched to like using VI probes to do this, which again, a well-calibrated VI probe has the same impedance accuracy as a VNA, or very, very close. You can fully map out a matchbox in 15 minutes. So you can have a huge improvement in efficiency by doing it this way. And we have customers who've set up Raspberry Pis communicating with our sensors to do all this automatically very, very quickly, and huge change in productivity in these matchbox apartments or refurbishment places. So again, we have videos on this and how-to documents on this. You can contact us and we can give a lot more detail on how to do it exactly. Right, so let's talk about plasma applications. That's the main topic of the talk, and that's what we spend the rest of the slides looking at. So let's just give a little bit of context. There's challenges facing future product nodes in the semiconductor industry. There's issues that have existed for a long time that still exist. So chambers not being so well matched. You have invisible wear and tear on chambers that can cause wafer defects. So what I mean is there's, I mentioned, say, cables or transmission line after the matchbox. They go through heat cycles. They degrade over time, and it's not something that you can clearly see by eye. There's no burn mark. There's no discoloring, but something has changed with it. Like there might be an invisible oxide layer or something. There's a lot of invisible wear and tear on tools, which is hard to diagnose that they're there. Also, developing these really, 5 nanometer processes or whatever on R&D lines, moving those to production lines is getting very, very challenging because your windows of acceptance, like what's an acceptable variation of the tool, are getting narrower and narrower. Sometimes as well, people are using the previous generations of tools for new processes, which lack basic diagnostics. And what my message is, if you want to monitor a plasma process, you've got to monitor the plasma directly. Okay. I also just want to give a little warning. Why can't you necessarily rely on some normal diagnostics? I've spoken with many, technicians and plasma process engineers over the years, and it's surprising what they rely on to keep yield up. So, for example, they rely on power measurements from the generator. And as I said, they're not reliable because the power actually reaching the plasma changes due to the matchbox. Even different matchbox temperatures have different efficiencies. So, that's, they do their best to make all their generators match, but their chambers aren't matching because the matchboxes aren't the same. Things even like pressure monitoring is misleading. Like tools often have like a closed loop pressure control system, so they'll open up the throttle valve or change the skims or whatever to make sure that the pressure stays the same. But that hides gas flow issues or hides leak issues and so on. And what I'm hinting at here is that you can actually, by monitoring the RF, you can see these. Some people monitor the tuning caps and make sure they're consistent. The tuning caps depend on the plasma impedance, but this is only a rough guide to the plasma impedance. It's quite coarse. Like there are some matchbox makers who basically provide a table with their matchbox saying, if you're in these tuning cap positions, your plasma impedance is this. But that's really not accurate. Like if you want to make sure your process is the same every time, you want to know the actual complex impedance and you want to know it to like decimal places, not a percentage on a tuner. Okay. And the message I want to give is that if you're not monitoring the plasma, it means you're not controlling it. How can you control something without monitoring? Okay. Or if you're trying to monitor it if you're trying to control the process without monitoring it, you're doing something expensive, right? You're losing wafers to learn things. Right, so let's start off with the simple plasma applications, okay, before we go to the complex ones. So I mentioned earlier on that, you can actually know a lot about the ion energy impacting the wafer on an RF biased, electrode just by looking at the voltage, okay? So as a general rule, the average ion energy is approximately half the peak-to-peak voltage as measured by a VI probe. Okay, so I have a real example here. For those of you who didn't attend the last webinar, which was all about ion energies and different tools under different conditions, this is this blue line here is ion energy distribution function. The bottom axis is not clear, but this is a case where the VDC is measured at like minus 1,100 volts. The ion energies are, in and around that value. So this is, how many ions at different energies, and this is going from 0 to 1,500 EV on this axis. So most ions are at, this energy due to the RF bias being applied, and then there's a tail that's caused by, collisions at different pressures and so on. So certainly in low pressure conditions, approximately half the peak-to-peak voltage you measure will tell you what your ion energy is, your average ion energy is. There's more sophisticated models than that, of course, but just as a very simple application, that's a quick way of getting good results. This data here is from a VI probe. The blue line is the voltage waveform, and the red line is current waveform. Obviously, on the generator side, you have perfect, if the generator is working well, you have a perfect sine wave for the voltage and a perfect sine wave for the current, and there's zero phase between them, so they're completely overlapped. But on the plasma side, there's a larger phase difference, and you get these distortions in the waveform due to plasma emissions. If we don't run out of time, I will go into the physics of this and the applications of this. But that's a very simple thing. The voltage will give you the ion energy. Okay. What about the current? So with the current, you can actually get ion flux, right? So when a VI probe is measuring current, it's actually a complex current. If you think about it, there's actually a real and imaginary component, or you can think maybe active-reactive component. I'm not sure what the words are, but essentially, yeah, the current that it measures has a complex value, and the real component of the complex value is basically like the real DC current. passing through the probe. And that DC current passing through the probe is obviously directly related to the ions hitting the surface. So more ions hitting the surface, higher DC current. And if you take the real value of that, of the current of the probe, divided by the surface area of the electrode, that's ion flux. And that's linear with etch rate, provided the ion energy stays the same. So if the ion energy is constant, if your ion flux increases by 10%, your etch rate increases by 10%. Okay. And there's various papers showing this, like not just etch rate, but also depth rate. So like here's ion flux and depth rate plotted on the same graph. They're completely linear with each other. So imagine with one of these in place, you can make sure that your ion energies are correct, because in some processes, like say dielectric etch, if they're not high enough, they're not etching. In other processes, if the energies are too high, you're damaging the surface, like maybe in a polymer deposition or something like that. Okay, so so this is quite a powerful application. Let's move on. I mentioned earlier, direct power and impedance monitoring is achievable. So if you have a VI probe between the matchbox and the plasma chamber, you can directly look at what's the plasma impedance. And if you keep that the same every time, you get the same process every time. Okay. There are more, there are easier and more sensitive ways actually to do the same process monitoring. We'll get to that in a few slides. But you can see here, like say, using different frequencies, what impact that has, like on the plasma impedance, what impact that has on things like etch rates for sputtering and so on. That can all be monitored. You can also monitor things like if you have a pulse plasma, you can have a look at the evolution of the plasma during the pulse. So you can see, what the voltage is versus time current is versus time impedance versus time, and so on. So this will, again, give you the same information as I mentioned already. You can get a look at sputtering rates, or you can get a look at actual power or energy delivered to the wafer. Okay. Another thing you can gain with learn from these is you can actually look at the efficiency of power being delivered into the plasma, because the efficiency actually changes as a function of power. And especially if you're using an ICP tool, there's a transition from like E mode to H mode that has to happen. And if you want to make sure that happens, you can monitor all that with a VI probe, because you'd have a massive increase in transfer efficiency as you go from E mode, which is like capacitive coupling, to H mode, which is inductive coupling. Okay. Again, we have papers on this and a lot more details. I'm skimming a lot of details for time, but come to us afterwards and we can give you more info. It's also possible to correlate, it's possible to correlate VI probe data with Langmuir probe measurements. So like, the plasma potential, the electron density, the electron temperature, the ion density, using what's called regression analysis. So you can, kind of calibrate a VI probe such that you first use an invasive instrument to know exactly what the plasma is doing. Then when you take that away, the VI probe will, with your kind of calibration, you can then go and say, right, this is my plasma density in real time. This is my electron temperature in real time. Yeah, you can correlate all these parameters. So this is kind of skipping the physics, but this is a quick way of doing that. And we have published papers on regression analysis on how to do that. Again, come to us afterwards. But you don't have to do regression analysis to correlate these things. You can actually, these waveforms that these VI probes can measure, these voltage and current waveforms, can be used to actually turn your electrode into a Langmuir probe if you want it. So how you do that is very complicated, but we've demonstrated it. So impedance is something that we call the Plato probe system, which is a type of Langmuir probe. But actually what it is, in this box at the bottom here, is a VI probe, okay? And this is a transmission line, and this here is an electrode. So we've made the VI probe, the transmission line, and the electrode. We've done a special impedance calibration on this transmission line. And then by processing those voltage and current waveforms intelligently, and that's done using what's called the Sobolewski method and using what's called a boost Braithwaite probe method. By applying that to the data and by using some, pretty tricky analysis, but what results is from a VI probe, you can actually extract like a Langmuir style curve. Like this is data taken using a VI probe, okay? But this is Langmuir data. So this is, the ion region and the electron region and the transition between. So yeah, and with that you get the electron temperature and the plasma density. This is obviously hard to do, but we know how to do it. We've published on how to do it. And we've done comparisons between the VI probe technique and the Langmuir probe technique to compare electron temperature measurements and other things. And what's extra nice about this technique is because it's, a Langmuir probe is what's called a DC probe. So you're monitoring, you need to have a conductor in the plasma and so on. With this method, because it's an AC probe, if you're like depositing materials, you can measure these plasma parameters through the deposition, because that's just a capacity, it's like a capacitor, and a capacitor is a short to AC. So that means that you could have a chamber where you're doing depositing and etching and making the chamber very messy, but be getting real-time plasma density and electron temperature measurements from your powered electrode, okay? If you have a VI probe after the matchbox. So this is something we've demonstrated. We've made a product on it. There's publications on it. So this is like probably the most powerful thing you can do with a VI probe. But of course, it involves a lot of work on the tool. Basically, you have to do some calibrations on the tool. So next, I want to go into something a bit more complicated. Okay. So I mentioned that with a VI probe, you measure the power, you measure the complex impedance, you measure the voltage, current, and phase. But the other thing is, a plasma itself emits its own RF. So what's coming from the generator is not all that's there. You actually get what are called harmonics. Okay. So I want to explain a bit about the physics behind harmonics and what they enable, because they enable some really surprising applications. Okay. So let me talk you through it. We should hopefully get it all done in 10 minutes. So the plasma, in the simplest term, is a conducting gas. And you can actually characterize the behavior of a plasma as an equivalent circuit. So you can actually treat a plasma like a circuit. So I've drawn one here. So this is a voltage supply, but it's basically a generator. The 50 ohm region represented by a 50 ohm resistor. You have a matchbox, which has its two tuning capacitors and an inductor. And then we imagine a VI probe here. And then the plasma can be modeled as a combination of capacitors, resistors, and inductors. Okay. And when we talk about plasma impedance and plasma as a complex load, it all comes from these. Okay. So in everything I'm talking about going forward, just imagine that, if you want to think of the plasma as like almost like a wire, right? Imagine the free electrons in the plasma moving up and down with RF. Okay. So imagine electrons going back and forth through the plasma, and that will help you picture how all these things appear. Okay. And this is generally a safe assumption that it's just the electrons, because the ions don't really react too much to RF. I mean, provided you're above about 10 megahertz in typical conditions, the ions aren't reacting very much. So assuming electrons are moving through the circuit, what could we potentially learn? Okay. So let's talk about capacitances inside a plasma chamber. So a major source of capacitance are the plasma sheaths. So plasmas form a gap between, the central bulk of the plasma and the walls and the wafer and so on. There's a little gap, and that's called the sheath. So like, let's say looking at the walls, if like wall conductivity changes, or like because you're etching or you're conditioning the chamber, or you're etching something and it's sputtering onto the chamber, you get changes in the wall conductivity, and you get changes in the capacitance. So that means you can actually monitor this, if a chamber is conditioned correctly or not, based on the values you get from the VI probe. The sheath thickness depends on plasma density. So if for some reason your generator calibration is off, or your matchbox is off, or there's something that's affecting your plasma density, you see a change in the capacitance, you see a change in the plasma impedance. So if plasma density changes, you will see it with a VI probe. Additionally, this may surprise people, but the wafer itself is like a capacitor. Okay. So for example, if the wafer is not sitting correctly on the electrode, you get a totally different capacitance, totally different sheath shape, and you can detect that using the change in the impedance of that circuit. Okay, and we've set up alarms in facilities based on wafer misplacement alarms based on these techniques. Even things like charge buildup on the wafer may change the voltages, and so on. Another application actually is, because the wafer has a capacitance, if you're depositing on it or you're etching it, you're changing the capacitance. So that means that by monitoring the RF, you can actually monitor the progression of etching or the progression of deposition, which enables endpoint detection. So I'll show examples of that later as well. I mentioned there's like a resistor equivalent. So if you imagine the electrons moving back and forth, it's going to collide with particles in the chamber. So, at low pressures, like under vacuum, electrons can travel millimeters to centimeters depending on the pressure, but they're moving fast, so collisions happen often. So in other words, this resistance value will change with pressure changes. So if your pressure gauge is not calibrated correctly or if there's an air leak, you can actually pick that up using the sensor as well. Yeah, let's move on because we're running a little low on time. So here's again this circuit, and I'm showing real data here. So this is from the VI probe. I mentioned perfect sine waves from the generator on, blue is voltage, red is current, and the phase here is practically zero. If you're perfectly matched, there'll be no phase difference between them. Okay, and then this was like real data measured in this. So I had a VI probe in the 50 ohm side and a VI probe in a non-50 ohm side, and this is what the data looked like. So you can see there's a distortion in the voltage wave and a massive distortion in the current wave. Okay. And this is all to do with this nonlinear load, this complex circuit. Okay. So of course, no one's going to monitor this. Like, you don't look at waveforms to judge what's going on in your plasma chamber. Okay. So there's a way of making this much easier. So with a VI probe, instead of using peak detection methods, I recommend you use Fourier transform methods. And that, if you apply a Fourier transform to a waveform, you go from time space to frequency space. So that means that you get a spectrum. So what I have here on the left is a voltage spectrum, and on the right is a current spectrum. And the first bar represents 13.56 megahertz, and the second bar is 27.12, 40.68, and so on. Again, the fundamental frequency comes from the plasma, and all the harmonics come from, the fundamental frequency comes from the generator, and the harmonics come from the plasma. Okay. Yeah, and so changes in that circuit, it will change the impedance that you measure, but these harmonics are really sensitive to changes in that impedance. So, and they're specific, are specific to the different things that change that I mentioned on the previous slide. So by monitoring these harmonic levels, you can get really high sensitivity on plasma chamber changes. And that's usually what we recommend really for process repeatability monitoring and so on. So I'll very quickly say you can do chamber clean and endpoint detection. So even if power stays the same over the process, if you look at the harmonics at the start and at the end, you get totally big changes in the harmonic spectrum because the cleaning happened. Okay. There's also publications looking at low area endpoint detection. So that's a challenge of the industry, monitoring below 5% or below 1% of the wafer being etched. Optically, that's really difficult now. But with RF, there's publications on you get at least twice the sensitivity. But from my own experience, when chambers where optical struggle to get, below 2% of the wafer being monitored, we've demonstrated well below 1% or even below 0.1% of the wafer being etched. And again, by this capacitance change of the wafer, and then by the corresponding harmonic and phase changes and so on that happens, you can judge that the process has finished processing, like that the endpoint is the etch is done. So I think this will be very powerful for the industry going forward. And I think I will stop there and open it up to questions.
Sure, and can I just say at this point, the question, we're still open to take questions, because if we don't get to answer them today, we'll certainly get back to you, in the next couple of days. And also, I know one of the big questions is, will we get a copy of the slides? You will, and you will also get a copy of the recording, but that may take about 24 hours. So everybody that's here today will get all of that. Thanks, Tom. A very long presentation again. You got a lot in there. I'll just go to the first question here. In RF plasma systems, the hot electrode requires DC self-bias. The ions are accelerated towards this electrode due to self-bias. So I think
Yeah.
that their energy will be more dependent on self-bias rather than amplitude of RF voltage.
Yeah, so that is true. Okay, so in this situation here, when I mentioned the peak-to-peak voltage, there's also the VDC, but it's more complicated. So, for example, plasma collisions may mean that the actual energies are lower than this. And the other thing is that when RF is present, you get peak splitting. So I didn't go into detail here, but with the VI probe data, you can actually glean a lot of information about the peak splitting. So in this case, I think this was 13.56 megahertz, so there's very little splitting. But if you're using something like 400 kilohertz, your ion energies are very, very broad, and your average energy is not so useful because you have lots of ions at a very high energy and lots of ions at a low energy, and then a kind of saddle in between. So, PDC will give you an idea about the average energy, but with this data, you can actually gain a lot more. So I only mentioned a simple model here, but you can go a lot deeper and get a lot more information about the. I know actually I have clients who've gotten the full like ion energy distribution function from the VI data, which gives it's a lot more informative. But again, yeah, if you have the VDC as an output of the on your tool, then that is definitely informative of the ion energies. But be careful at low frequencies. Yeah.
Okay, is it possible to separate out plasma response, power dissipation, what part of the circuit is causing reflected power, etc., versus the other parts of the total circuit, such as wires, contacts, etc., using a VI probe? Or do you only get information about the total circuit?
That's a great question. Let me go to. So I don't. It's not in here, but we actually have a document which is basically on how to use VI probes in a fab for troubleshooting, and it goes into a lot of detail on like measuring at different points and what you can learn from measuring at different points. Okay. So for example, regarding reflected power, sometimes if you're just looking at the reflected power on the generator, or if your FTC system on your tool is only reporting 1 second, you can actually miss that during the initial ignition. You're getting a big spike in RF power, and that spike is getting larger and larger, and that's indicative of issues in the matchbox, right? If you're looking at data fast enough, you'll actually start to see these things you wouldn't normally see, or you'd see that it's very noisy and there might be small levels of arcing happening in the match or happening in the tool. So the answer is actually yes. By measuring at different points, you can learn where an issue is. So for example, I have data which I can't show now, but I could show on a call, where we could see that arcing was happening, and then by changing the measuring point, we actually determined that the arcing was happening inside the matchbox as opposed to inside the plasma chamber. In terms of going deeper than that, so for example, what specific component is causing the issue? That is possible. At the end of the presentation here, I was going into harmonic generation, and I deleted a whole bunch of slides because I knew we'd run out of time. But the harmonics tend to react uniquely depending on the part that is causing the problem. So we've done experiments on a tool where we had a VI probe there, and over a period of a day or two, basically induce faults on the tool. So like add in nitrogen to simulate an air leak, make it so that wafers are not sitting correctly, make it so the shower head is blocked, make it so an MFC doesn't open on time, blah, blah, blah. And then from all those, and like power and skim changes and so on, and from all those, you can actually, by looking at this, the harmonic response, and there's algorithms to do this quite quickly, you can see that there's a unique pattern, a unique response depending on what part fails. So it is possible. You have to be clever with the data, and it takes, you have to have a lot of data to do it efficiently. To give one more example, so there's a number of high volume production facilities where I implemented an alarm system based on VI probes and based on wafer misplacement detection, because that was a big issue. And the VI probe would say, okay, based on the data, based on the impedance, based on a few other things, the plasma is not good, turn down the tool. But then based on the specific response of specific harmonics, you can then also say there's a problem with the plasma, and it's definitely due to wafer misplacement this time because the harmonics have responded this way. But that's complicated, difficult, but we have demonstrated it before. Okay. Yeah.
Thanks, Tom. A lot to answer. Could I just say again that if you'd like to continue a conversation afterwards or have a specific conversation around various issues you have, just send us a chat message or an email and we can set up a meeting with Tom. Another question here, Tom. How fast can you get data from sensors?
So yeah, report rate is important. Like I said, a lot of FTCs run at like once a second. And there's various sensors on the market that go different speeds. But on our sensors, by Ethernet, you can go up to 10 times a second. By EtherCAT, up to 50 times a second. Get all the harmonics, all the power, all the impedances, and so on, forward affected. And over USB, you can go up to 500 times a second. And you can type in a report rate. So if you want data every 100 milliseconds or every 10 milliseconds, with the very latest probes that we sell, you can set that, and you can say, yeah, I want data every 10 milliseconds on the reflected power, and I want to have a close look at the ignition. I mentioned also that you can do arc detection. So with the way VI probes work, they can run very, very quickly. So, with pulse plasmas, we can actually look on the microsecond level. Like we can look at the pulsing up on 1 microsecond time steps. And you can make arc detectors with these. Again, you can look at the voltage and current data so quickly that you can look, has an arc happened because there were a massive change on a microsecond time scale. So the VI probes can go very, very fast, actually. Yeah.
Okay. How would you increase the efficiency of the matching network if the tuning load capacitor is already approached its maximum value?
No, that's a tough one, but one of our RF experts in impedance, Sami, has written a document, we haven't published it yet, which actually talks about that and gives a real example. So just send us an email, we'll make sure you get that. But basically it comes down to, if you know this matchbox range and you know where your plasma impedance is, you can actually do a calculation that says, right, in order to move this range in a certain direction, a capacitor value has to change by this, or you have to change your inductor from this value to that value. So that's fairly easily calculatable. Once you have the data of the matchbox range and the plasma impedance. So again, it's just about changing a capacitor and inductor, and that's it. You can get massively better efficiency because you're within the matching range. Yeah.
Okay. What is a PCA?
PCA is a principal component analysis. And that's a way of analyzing data so that you kind of bucket data depending on its response to something. So by using PCA, that's one of the ways that you can, let's say you're monitoring all the harmonics for a system, and you're trying to detect a specific issue like an air leak. If you use PCA intelligently and a bit of linear algebra, a PCA plot can kind of tell you, okay, you can see things drifting, but depending on how it drifts in PCA space, you can actually say what the fault is. This is very complicated, but basically, assuming that's what you mean, PCA is principal component analysis. It's a method of applying statistics in a way that gives you information on what's changing. Yeah.
Super. Is calorimetry a correct method to measure power dissipation in plasma? Power deposited into the plasma will also be lost by the particle losses on the wall.
Oh yeah. So I mean, if you want to, this comes down to plasma efficiency. There's a lot more you can do there. So for example, I mentioned in a different slide, I'm going to remember where the slide is now. Yeah, this one. So I mentioned actually with delivered power, so the calorimetry is only to calibrate this probe. Like, it is not a calorimeter. It doesn't have like water on board and measuring heat or whatever. It's all done by, you have a remote pickup. It picks up different strengths of electric and magnetic fields, and we make kind of a database of how all that responds versus power. Okay. and versus impedance and everything else. So this makes this equivalent to a calorimeter in a way. Okay. So if you know to deliver power to the plasma by using what are called Lieberman global models, although they're only applicable over a certain range, but you can actually even get this sort of electron ion loss efficiency. Like there's these what are called power balance models. So by looking at power input to the chamber, and with a bit of extra maths, you can actually judge what's being lost to the walls and what's making it to the wafer. I kind of get the point. Like if you care about the what's being delivered to the wafer, there's a bit more work to get it exactly right. Although I have a feeling with the voltage information, the current information, that will give you more relevant. Like if you look at the real component of the current, for example, and look at the voltage on the electrode, that's probably telling you exactly what's going to the wafer alone, because it's, you know, I think that would actually work. Yeah, I'm thinking out loud here, but yeah, with the real component of the current and that, you could get that information, I think.
Yeah, again, we can set up a chat offline there if you wish to pop us an email. So how do you correlate which harmonics relate to which change, pressure, wafer, etching, etc.? Do you do that experimentally?
Good question. There's many ways of doing it. You can do it purely by physics. So there are people who are, it's a PhD level project, right? But you can actually do it by physics if you want, if you know enough about the tool, or like if you make what's called an equivalent circuit model for the tool, which is possible. So if you try to put together, like if you have an electronic engineer, you kind of talk them through a tool and say, there's the plasma sheet, it's typically disk capacitance, there's a wafer, we measure disk capacitance, blah, 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 blah. It is possible to build a true circuit model, equivalent circuit model of the, plasma. We've had clients do that, and that gave them full predictive abilities on how harmonics would behave as different things changed. So you can do it, by physics and by electronic engineering techniques, but that is very hard. And it's like you said, PhD level project. Easiest way is experimentally or historically. So what do I mean by historically? You can have you could have one of these passively collecting data over a long period of time, and then go back and analyze the data as each fault was detected, and then do it that way as well. Experimentally is the fastest way, kind of without damaging the tool, cause the problems on the tool, right? So like I said, disconnect the shower head, or change a flow rate, or introduce nitrogen as to simulate an air leak or something, and see how it responds experimentally. It's a bit of work, but it's done before.
Okay. So how do you account for non-zero length and non-50 ohm line between matchbox and electrode?
Yeah, this is the hard part, right? So the cable is complicated, but after the matchbox, you have large changes in everything along that transmission line. Okay, so as a general rule, you want to be as close, like if you're taking a measurement, you want to be as close as possible to the electrode. It is possible to totally take into account, between the VI probe and the surface of the electrode. You do that by, if you have the ability to hook a VNA up between where the VA probe is going to be and the surface of the electrode, and you get what's called the S parameters. With the S parameters result in a matrix, and if you multiply the octave data by that matrix, it actually tells you what the data is on the surface of the wafer. So this is a thing you could do, this impedance transformation. And in fact, we do that on our sensors. So the sensing elements in the center are right in the octave sensor are right in the middle. They're in the center of the body. But the data we report is the data at the output of the sensor. Okay, so we've done already that kind of transmission, matrix. So it is completely possible to do that transformation. It's typically not needed if you can get the sensors close to here. Otherwise, you may have to make some assumptions. Because the voltage, current, and phase actually change and can change dramatically along the transmission line after a match. But I would also say flawed data is way better than no data. Okay, or let's say slightly off data. Like if you can only put a VI probe at the output of the match and you have a transmission line, that's way better than having no data after the match. And also, when you're monitoring changes, the absolute values don't matter as much. Like you're going to monitor plasma performance, it doesn't matter if you know exactly the power delivered to the surface of the wafer, as long as you can monitor the changes.
Okay, thanks. Well, we're getting lots of questions, and just to assure you that we will get back to you over the coming days with an email, because I know Tom is not going to have all the time as we're just about running out. But one final question. When measuring voltage and current with separate V and I probes, how can I obtain the power from the measured voltage and the current curves? How do I know the phase? What else should I pay attention to?
I mean, that's a question I can't really answer.
Well, think about it and get back to you.
There's a way of doing that, but I can't think about it off the top of my head. All I can say is, though, that the phase measurement is so important. Impedance actually owns a bunch of patents on getting really good phase measurements. So we've developed techniques to really nail that down, so we can measure at 89.6 degrees, 89.7, and not have a problem. So phase measurement can be a bit tricky, but it's possible. Yeah.
You mentioned that active current measurements may be processed for getting ion currents, but what about the electron currents? How are they separated?
Good question. I haven't thought about it, because generally the ion processing is what people care about. The way I'd go about that would probably be using, like, say I mentioned that you can get the ion flux, so there's a few different ways. So if you use the Plato probe technique I mentioned, like I said, that gives you ion density and it gives you electron temperature, so you can use that. Or if you have the ion flux, if you have the ion flux and you know the electron temperature, you can work out what the ion density is via the bone velocity. So then you can maybe make the assumption that the ion density and the electron density is the same. But in general, if you want to know what the electrons are doing there, I'd have to think about it. I think the Sobolewski method actually would pull that information out. The method I mentioned for how we get the electron temperature and ion density from the VI probe. So yeah, probably the Sobolewski method is the way that you can separate the ion flux from the electron flux, actually, because we specifically look at a point where we have ions only and no electrons. Yeah, so that is extractable from the waveform. You'd have to contact me for the paper. That is extractable. Yeah.
Okay, look, lots and lots of questions, and we've just run over the hour, but please do, give us an email, and we'll try and set up a meeting separately with Tom just to get through all of those. Could I just mention that in the next few weeks, we will be sending out a newsletter, and in that newsletter, you will have access to the past 2 webinars that we've had also, because I know we've had huge interest there. So be on the lookout for that. And again, in the meantime, if you have any questions, please pop us an email. Many thanks for coming along today. It's been a fantastic response, and we look forward to seeing everybody online again in the new year. Thank you very much.